All right, so yeah, let's talk about precedence graphs. This is just kind of an example of something we can use graphs for, uh, computer sciencey wise. So let's write some instructions that have potential for parallelism. Let's just assume these are integers and we're writing in C, um, and I equals 10. J equals 12, K equals -2. If I is greater than J, K equals K times 2, I equals 5, print I, comma J, comma K. Random program here. Put good old line numbers on these. And let's look at what depends on what. So these first three statements are not dependent on anything. They can execute at any time. So we make a vertex for each statement. And I'm just going to number them with a statement number. And then down here in statement 4, we have something that depends on the values of I and j, which are set up in statements 1 and 2. So statement 4 is dependent on statements 1 and 2. And this is probably a directed graph, right? But I'm drawing it, from top to bottom. But there's probably, makes more sense thinking of all of these as directed. So this is representing the fact that, I could execute instructions 1, 2, and 3 at the same time. I can execute instructions 3 and 4 independently of each other, but I can't do instruction 4 until I finish instructions 1 and 2. And it's just capturing the fact that 1 and 2 set up things that will affect the behavior of instruction 4. All right, instruction 5 should modify the value of k. Well, before we can do that, we need to have initialized the value of k. And we also need to have evaluated this if statement. And so statement 5 really depends on execution of the if and the initialization of k. And this is not capturing the fact that we might or might not perform instruction 4. I'm just looking strictly at dependence, right? If we're going to execute instruction 5, what has to happen first? And then instruction 6 needs to happen after instruction 4 is evaluated, right? Because we need to know if we should be doing this. But instruction 6 and 5 can happen at the same time. Or 6 could happen first, or 5 could happen first. In other words, these two instructions can get flipped. No impact on the final result. And then instruction 7, we need to print out the values of I, j, and k. So the last time that I gets a value updated is well, so this, yeah, I shouldn't have used an if, because I can't really make 7 dependent on 6 if 6 is not going to happen. So yeah, well, let's just leave it at that. But anyway, it's a way to capture the idea of precedence, right? So something needs something else to happen first. You can capture it by drawing an edge from the thing on which it depends to the thing that depends on it. Dashed arrows? Yeah, I mean we could define a way to capture this, right? But then we're actually talking about something more than just precedence. We're talking about drawing a graph to capture the flow through a program, and that's an entirely different thing. But let me do one like this. All right, so there's an example of a graph. Right, a precedence graph. So this tells me that I cannot evaluate the value of I. I can't execute this instruction until I've done this initialization for I, but I've also done this calculation of z, which I can't do until I've initialized j. And so if I think of my uninitialized nodes as happening at time 0, I can start doing some graph theoretic analysis on this. And for example, if I find a series of edges with a total, of 20 edges from some initial point to some other instruction, I know that my program is going to take at least 20, time units to complete, because I cannot execute that instruction until 19 things before it have executed. Whereas in this case, I know my longest dependency is 1, 2, and if I had unlimited processing power, I could do these at the same time, and I could do this, and this, and this and this at the same time, right? And then I could do this one. So 5 instructions, I could do it in the time it would take to execute 3. So we can analyze parallelism, and we can also use this inside the CPU to break up the instructions, rearrange them, do them in pieces, and so on. That's all computer architecture aspects of this. Here we're just looking at it as an example of a graph. Yep, ij parallel, kz parallel, x parallel. Exactly. And when people started working more with computers and thinking about how to speed them up, there was some excitement at the idea of, what if we got 100 computers working at the same time on one problem? We could take these things that take an hour to do, and we could solve them in 36 seconds, right? 100th of an hour. And that's a really exciting prospect, but that really doesn't work. Parallelism does not play out that way in most cases. If you have 2 CPUs and you have a nice problem, you might be able to do it almost twice as fast. If you have 100 CPUs, your problem will probably take longer than if you ran it on a single CPU, because there's overhead, and there's communication, and there's contention for resources, and you're sharing data sometimes, and if you have 100 CPUs all waiting for data from each other, you can end up with a slower overall process execution than if you had fewer CPUs. So parallelism is kind of a holy grail. It's a really tricky thing to make work in general. Now there's some problems that work really well for this, but in general it's hard to parallelize, and it's even harder to have something that automatically parallelizes for you, like inside a CPU. But Intel processors do a really good job of that. All of the hyper-threading and so on works pretty well. All right, other questions? So a couple of comments. One, there should be something that's been up in Canvas for at least a week now, asking you to do a course evaluation on the course and on me in Canvas. Please find some time to do that and submit it. Particularly with online courses, it's generally kind of tricky to get people to respond to these things. When we meet in person, usually what I do is on one class, I'll end the class 20 minutes early and say, hang out in the classroom and fill out those online questionnaires. And I guess I could do that here, same thing, but it seems kind of silly since we're remote anyway. But if you can find some time to fill those out and submit them, please do so, because it really helps with improving the course over time, and finding out if there's some kind of problem with an instructor and so on and so forth. Um, and yeah, the bulk of today's lecture is talking about circuits and paths and Euler and Hamilton and then Djikstra. And those will be the last pieces that you need for the homework. All right, well, let's jump into that, and then if questions come up along the way, you know, we can loop over those. So let's talk about paths. And we started this somewhat informally on Wednesday, and I'm still not going to get very formal. But you know, if you have a graph, and I'll just label my vertices A, B, C, D, E, F, right? What do we mean by a path from A to F? Well, we could mean, for example, traveling, starting at A, along this edge to C, and then along this edge to F. And that's a path. There's another path, which we would get by starting at A and traveling to B, and then traveling to D, and then traveling to F. And if our paths can contain loops, then we could have yet another path by starting at A and going to C and going to back to A and down to B and out to D. And we could go to F and go to E and go to C and then go back to F. And that's a much longer path, and it includes loops. We go back to places we've seen already, but it's still a path. All right, so we're going to talk about simple paths. We're going to talk about paths that don't cover the same edge more than once. All right, so simple path. Don't travel along an edge more than once. And I'm not going to give you a formal definition of a path. Just think of it as, you know, a path from A to F means starting from A, follow an edge, right, with initial vertex A and some terminal vertex, and then follow an edge with the starting vertex of that first edge's terminal vertex, and follow to the terminal vertex of that second edge, which should be the starting vertex of a third edge, and so on until you get to an edge whose terminal vertex is F. That collection of edges in that order gives you a path. But really just start, you know, and go boink, 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 follow it around. All right, we're going to talk about simple paths, so we're not going to allow ourselves to go back over an edge more than once. All right, so there's a particular class of simple paths. Is there a way something that looks like a path wouldn't be a path? No, not really. There's not really a lot of tricks here. But you know, what would not be a path? If we started from A and we went to C and then we tried to go to B and then we went to E and then we went to F. Well, that's not a path from A to F, because from A to C we can go like this, but there's no edge connecting C to B, right? So I mean, we could jump to this vertex, we could teleport or something, but it's not considered a path because there's no edge connecting C to B. If you can teleport, all the stuff is easy, right? So it's just putting restrictions on it. All right, so we're going to talk about what's called an Euler path. Euler, the mathematician, Euler's theorem, all that sort of stuff. An Euler path is a simple path that contains every edge. So we're always talking about some sort of graph, with a collection of vertices and a collection of edges. So an Euler path through this graph is a simple path that contains every edge in that graph. And an Euler circuit is also an Euler path. But it's got to come back to where it started. So it begins and ends at the same vertex. So let's look at some examples. So is there a path we can make through this graph that covers every single edge and doesn't have to go back over an edge more than once? And we're not specifying where we have to start or where we have to end for an Euler path. We simply need to hit each edge once. Okay, so people are saying yes. So let me label these. And somebody give me a path through here. So just give me an ordered list of vertices that will correspond to a path. A, B, A, C, D, E, C, B. So A, C, D, E, C, B. Or A, C, E, D, C, B. Alright, so that does have an Euler path. And it's got multiple ones, right? A, C, E, D, C, B. And if we start at different vertices, we can certainly find other ones. All right, does it contain an Euler circuit? Yeah, so we can take exactly any of these Euler paths, and most of them end up pretty close to where we started, and so we can draw in an extra edge and get an Euler circuit. So for example, ACE brings us down to here, and then D, C, B, and back to A. So there's a graph that has both. Alright, let me draw a different graph. And is there an Euler path through those? So in this previous one, ABCA would not be an Euler circuit because it has to be an Euler path, which means it has to contain every edge. And ABCA would not cover these edges down here. Alright, so what do you think? Is there an Euler path through this graph? Not that we can tell. And in fact, there is not. We cannot cross an edge more than once. That's the Euler part of it. It's got to be, or that's the simple part of it. if we could cover edges more than once, we could go like this, and go like this, and go down here, and then go across, and come back up, and then pick up that. But yeah, if it's simple, turns out there's not an Euler path. And if there's not an Euler path, there can't be an Euler circuit, because an Euler circuit is an Euler path. So this one, no joy at all. Let me show you one in the middle. So 5 vertices, A, B, C, D, E. And sometimes I like drawing graphs where I don't actually connect the dots, because it makes it easier to see the dots without having to draw a big old dot. But this is just, you know, plain old graph like we've been working with. All right, is there an Euler path through this? Yeah, what would a path be? A, B, D, C, D, E, C, A, B, D, C. A, B, D, C. I don't think we can go from D to C and back to D, because we would be traveling this edge twice. Okay, so let's see. A, C, E, D, B, A, D. So start here, and let's travel A, C, E, D, B, A, D. That looks like a good Euler path. And there's some other answers coming up in chat, and those look good, I believe, too. So yeah, we can start at one point and travel and visit every edge without visiting an edge twice, and that works fine. What about an Euler circuit? Can we find an Euler path that starts and ends at the same point? And yeah, the answer for that one is no. If we take this path that we just followed, we start at A, we end up at D. There's no way to get back to A. Oh, we needed to hop up C also at the end. All right? But there's no way to get back to A. Now that's hard to prove, right? I mean, we can try different paths, and on a computer we could try every possible path and exhaustively show that none of them start and end at the same point. But by just kind of playing around with it, we can sort of convince ourselves, just like in this case, we can kind of convince ourselves that there's no Euler path possible. But it's a bit of a slippery thing, right? But you play with these, you start to get some intuition for it. So we do have a theorem. And this is credited to Euler. And there's a history to this. There's a series of bridges in a town in Europe. And I think it's 7 bridges connecting different islands in this little area of town. And people often wondered if it was possible to start at one end of a bridge and cross all the bridges without repetition. And that's, at least according to the folklore, right, that's the original graph problem that inspired this result, and is credited to Euler. So here's the theorem. I'm not going to get overly wordy on here, but in a simple connected graph G equals V comma E, there exists an Euler path right? If and only if exactly 0 or 2 vertices have odd degree. So this is the magic to knowing if there's an Euler path. Count the degree of each vertex. If you have 0 or 2 vertices with odd degree, you're good to go. So what's the degree of each vertex here? 2, 2, 4, 2, 2. No vertices with odd degree, you're guaranteed there's an Euler path. On this graph down here, degrees are 3, 3, 3, 3, and 4. You have 4 vertices with odd degree, guaranteed there's no Euler path. And on this middle one, degrees are 3, 3, 2, 4, and 2. Exactly 2 vertices with odd degree, you do have an Euler path. So we have this really simple criteria for knowing if there's an Euler path through a graph, and this also tells us if there's an Euler circuit. So there exists an Euler circuit if and only if no vertices have odd degree. In other words, all vertices have an even degree. And so here, you know, we had 2 vertices with odd degree. That's okay to have a path, but it doesn't give us an Euler circuit. In this original one, all the vertices had even degree, so we did have a circuit as well as a path. And that's a really simple criteria to apply, right? It's really easy to calculate the degree of each vertex. If you have these things stored in an adjacency matrix, just add up, you know, each column or row and calculate modulo 2. That'll tell you if the number is even or odd. And so if you want to find an Euler path, make sure you have either 2 or 0 odd degreed vertices. And it turns out that once you satisfy this criteria of having, say, 2 odd numbered vertices, odd degreed vertices, if you start at one of those odd vertices and plan to end at the other odd vertice, it's extremely easy usually to find a path. It almost does the work for you. So here's the one that I learned this on as a kid. Right, and you want to draw this house without lifting your pen, basically. That's what it means to be able to find an Euler path. So if you calculate the degree, that's got degree 2, that's got 4, 4, and these are the odd ones with degree 3. So simply start at one of the odd vertices and go from there. And there's so many different ways to do this. All right, So those are Euler paths. That's trying to visit every edge exactly once. The dual to that is a Hamilton path. And a Hamilton path is a travel through a graph where you try to visit each vertex exactly once. So a Hamilton path visits each vertex exactly once. And for Hamilton, you're allowed to cross edges more than one time. But your goal is to visit each vertex once. So we'll do some examples of this. And we can define a Hamilton circuit exactly like we did a Euler circuit. A Hamilton circuit is a Hamilton path that starts and ends at the same vertex. So sort of the obvious thing you'd expect. So so let me label these. And is there a Hamilton path through this graph? Sure. What would a sample path be? DCBAE. All right, just start here, go down, down, over, up, and you visit each vertex. And Hamilton circuit. D, E, A, B, C, almost. D, E, A, B, C. I come back to where we started with a D. Good. All right, start here and go down. Boom. We didn't visit these edges. We don't care. We're only trying to visit vertices. And that's pretty easy to do in this graph, right? There's a lot of different ways to do it. All right, let's try this one. All right, is there a Hamilton path? Yeah, A, B, C, D. We can go over, down, over, we're done. What about a Hamilton circuit, though? So this seems harder to find, and in fact there is no Hamilton circuit through this graph. And the reason it doesn't look like one is because, well, if we start with A, right, and we visit, right, there's no way to get back to A. The only thing that connects A to anything else is this edge, and once we visit that edge, we can't go back on it because it's not a simple path. So we can't start at A. And if we start at any of these other vertices, at some point we've got to visit A, which means going along this edge. And then again, there's no way to get back. And since we're not starting at A, we've got to get back to wherever we started to make a circuit. And that would require crossing this edge twice, and it's not simple. So we can kind of convince ourselves that there's no circuit available in here. But trying to do that more generally is really difficult. And in fact, there's no simple criteria to tell us if there's a Hamilton path or a circuit through a graph. Whereas with Euler paths and circuits, we have this simple notion of looking at the degrees of the vertices and counting. All right, so let me show you a bad example. Well, it's a good example of something bad. Right, so this one we got no hope, and it's the same kind of situation here. If we start with this vertex, right, then the only way we can get to this vertex is from here, and then we can't get back. And the only way to get to this vertex is from here, and we can't get back. So we can't have picked up both of those vertices. And if we start at something that's not one of these edge vertices, right, we can go out and pick up one of them, but there's no way to get back, so our path would have to end there. So this has no Hamilton path. And then certainly no Hamilton cycle, because a Hamilton cycle is a Hamilton path. Let me show you a little bit of a funny application example for this idea of a Hamilton path. This may induce headaches in some cases, so be warned. Let me show you a graph, and this is just, you know, a graph drawn on a piece of paper, but it may look three-dimensional, but that's really just an illusion. It's just a graph, but it's got connectivity like this. And this is not the part that induces headaches. All right, so there's a graph. I mean, it could be a three-dimensional graph, that's okay, but you know, this edge and that edge are not touching each other, whether this is a flat graph or it's actually a three-dimensional cube, which is what it looks like. But it's just a graph, all right? I'm going to label my nodes with binary codes, all right? So this is going to be 0, 0, 0. This will be 0, 0, 1, 1, 0, 1, and 1, 0, 0. And then this will be 0, 1, 0, 0, 1, 1, 1, 1, 0, and 1, 1, 1. And if I were to think of this as a three-dimensional graph, I'm thinking of a coordinate system like this. All right. Is that a right-handed or a left-handed coordinate system? Here's a pop physics quiz for you. Right-handed, left-handed, or no idea? Yeah, you got a 50-50 chance unless we're octopi, and then you got a 1 in 8 chance. Right hand, that is correct. So how do you know it's right-handed? Put your fingers in the direction of X and then curl them up towards the direction of Y and see if your thumb points in the direction of Z. Well, it does, so that's right-handed. If I try to do it with my left hand, there's X, there's Y, Z would have to be going backwards. So this is a right-handed coordinate system. Graphs don't have handedness, but coordinate systems do, and coordinate systems normally have nothing to do with graph theory. But I'm putting this on here for a particular reason. Well, Z can go up, right, if I draw X and Y differently. But it all depends on your point of reference, right? It's all relative. But if I swap x and y, I have a left-handed coordinate system. And then all of the stuff that you do in physics breaks, right? You have to do the dual of it. Your rules for finding cross products and that kind of stuff. You have to flip the signs. But anyway, that's the sidebar, just because it's Friday. All right, so is there a Hamilton path through this graph? All we have to do is visit each vertex, and so it's really not too hard. Yeah, there is. And let me show you an example. So let's start off here, and let's come over here, and then go up, and then let's go back, and across, and then let's go forward, and then down, and then back. All right, that's an example of a Hamilton path. There's other ones we could make. And so somebody just wrote out the coordinates for each vertex. So let me do that here. 0, 0, 0, 0, 0, 0, 1, 0, 1, 1, 0, 1, 0, 1, 1, 0, 1, 1, 1, 1, 0, 1, 1, 0, 0. And in fact, there's actually a Hamilton circuit where we could take our path from here and go back to where we started, to 0, 0, 0. Cool, same path. All right, I could have just copied yours then. Thanks. All right, why is this interesting to us? Because if we think of the coordinates of each vertex as being x, y, z, if we think of the label as being x, y, z coordinates, right? This first number is how far we've moved along the x. The second number is how far we've moved up in y. The third number, z, is how far we've come out in this direction. And since all of these edges are parallel to one of these axes, when we travel along an edge, exactly one of our coordinates is changing. For example, at this point here, we're at the point 0, 1, 1. When we move in this direction, that third coordinate z changes, and we go from 0, 1, 1 to 0, 1, 0. So yes, exactly. As we follow this path, we find that from one vertex to the next, only one bit changes. And if you look at the values written out here, that's exactly what's happening. From here to here, only this bit changed. From there to there, only this middle bit changed. From here to here, that least significant bit changed. And then from here to here, only the most significant bit changed. So do you remember what this was called in 250? Yeah, this is a gray code. I just Googled to see if it was an A or an E. It looks like it's an A. This is what we call a 3-bit gray code. So the property is that from this first number to the second, this is the only change. From the second number to the third, this is the only change. From the third to the fourth, this is the only change. Fourth to the fifth, this is the only change. And then from here to here, this changes. From here to here, this changes. And from here to here, this changes. And from there to the last number, only that changes. So this is useful, right? This is what we are interested in when we talk about state machines, and we want to have state machines without glitches in them. Remember, if you have a state diagram for a system and there's, this temporary state which says, launch all missiles, we don't want to accidentally bump into that state. And when we count in sort of traditional binary, like this, there are cases where, for example, from here to here, we have 2 bits changing at the same time. And depending on the order in which those change, we could inadvertently end up in state 3 for a brief instant. If this 0 changes to a 1 first, our value would be 0, 1, 1. We're in state 3, which is the, destroy all monster state. And we didn't mean to do that. We just wanted to go from state 1 to state 2, and then from state 2 back to state 0, right? And this is the glitchiest of all, right? This one and this one, because all 3 bits have to change. And so, yeah, the clocking can get you into problems if you have different path lengths coming from different parts of your circuit. Depending on when each of these 3 bits changes from their initial value to their final value, we could hit, almost any intermediate state for a fraction of a microsecond. But, that's possibly long enough to change the value of a flip-flop, and now we've introduced, a transient state in our transition. So a quick way to mitigate that to some degree is to order our states according to a gray code. And a gray code is really just an example of a Hamilton path through a particular set of vertices in a graph like this. So that's a little bit of a throwback to 250, because we never want to forget 250. All right, A is for America, E for everywhere else. I think that makes sense for gray. Although I don't know how I would interpret that for this. So I just Google on a side screen when nobody's watching. But for colors, that makes sense, yeah. The word is valid with either. That works for me. So yeah, this is a well, this is a sidebar, I guess, but talking about gray and gray, and being able to read those. So you've probably seen this. Right, so this is really trippy the first time you encounter it. But, for the most part, if you don't think about it too hard, this is totally easy to read, right? Even though, to a computer, trying to compile this, if this was a C program, it would just totally flip out. But, for whatever reason, based on how our brain processes information, right, we have no problem seeing what this says. Yeah, so we're wasting our time writing all those extra letters in between, right? So yeah, gray and gray, we know what we mean. All right, so next topic. This is the last topic really for graph theory. This is the notion of shortest path. And our goal is to find typically a path that visits each vertex, okay? And not necessarily a simple path, but simply the goal of trying to visit each vertex with as little travel as possible. So let me make some vertices. And so if we, let's see, we can also read much faster than we realize. Having to move our eyes to follow text increases how long it takes us to process. You can see this in many videos where they will instead just flash words on the screen right in the center. Yeah, that's totally true. Plus also, you know, it's pretty common to some degree move your mouth as you're reading, even if it's, you know, not moving full on, to be activating those muscles, and that actually slows you down. But I hadn't thought about the business of moving your eyes. But you can also, you know, by just looking at a screen, you can actually read everything that's on there without moving your eyes. But it, I think, takes some training and practice to do that. Yeah, well, Elon Musk's got those implants that they're putting inside pigs that, you know, will be available for humans soon. So then, you know, we can link in directly to CTC Link and you know, yeah, maybe that's why it's called CTC Link. Shortest path. So say we want to travel from this node to that node, and we could ask, how can we get there by visiting the fewest number of edges? Well, we could do 1, 2, 3, 4 like that. We could do 1, 2, 3 like this. We could do 1, 2, 3, 4 like that. We could do, you know, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 like that, right? So on a plain unweighted graph, right, shortest path is asking what's the fewest number of edges that it would take to get from one vertex to another. But when you introduce weights, right, this becomes more interesting. Right, so now what's the shortest path from, let me label this A, let me label this Z, shortest path from A to Z. And it's not clear, except that, you know, I chose these weights deliberately to have an obvious answer to me. So, you know, if I travel like this, that's 1, and 2 is 3, 4, 5, 6, 7 if I go that way. If I travel here is 1 plus 2 is 3 plus another 3 is 6. So that's a shorter path. If I travel 1 and 3 is 4 and 4 would be 8, right? 2 and 4 is 6 plus 2 is 8 plus 4 is 12 and so on. But if this is 12, right? It may be that this path, which involves 4 edges, is shorter length in terms of, you know, the weights than any of the paths that are only 3 edges, like 1, 3, 4 or 1, 12, 3. And so there's this question of how do we find the shortest path from one vertex to another. People don't want chips in their brains. Yeah, I agree. Can you imagine if, well, no, I won't diss on certain tech companies, but imagine if your least favorite tech company made these chips. That would be a bummer. Yeah. All right, so how do we solve this? So we've talked a little about algorithms, and we'll talk a lot about algorithms in CSE222. But there's a class of algorithms that are called greedy algorithms. And a greedy algorithm basically works by trying to solve the problem as quickly as possible. So if you want to make exact change, right, you've got a handful of pennies and quarters and dimes and nickels, and you want to know, what's the fewest number of coins I need to get, 37 cents. There's a greedy algorithm for that, right? Start with your 37 cents, subtract off your largest denomination, which is a quarter. So take off a quarter, that leaves you with 12 cents. You can't take off any more quarters. Your next denomination is a dime, so start taking off dimes. That leaves you with 2 cents. You can't take off any more dimes, can't take off any more nickels. Take off your pennies until you get to 0. So a quarter, a dime, and 2 pennies, that's your best solution. That's a greedy algorithm. Does not work for Djikstra, for shortest path, right? Because shortest path would say, well, well, actually, it would work. But let's suppose that this was, shortest path would say, well, first we should go here, right? And then let's go to the vertex closest to this, which would be here, and go to the vertex closest to that, and go to the vertex closest to that, right? And that would leave you with 4, 6, 10, 11. Whereas if you had taken the slightly more expensive initial path, the rest of your journey is short enough that you end up with 3, 4, 6, total distance of 8. So yeah, as someone just said in chat, there's an algorithm for this. It's called Dijkstra's algorithm. So Djikstra was a mathematician, early computer scientist, and this was an algorithm credited to him for finding a shortest path through a graph. And it's an efficient algorithm. There's brute force ways to do this. Right? If you start at this point, you've only got 2 ways you can go, this way or this way. So find your shortest path from here, find your shortest path from there, add the distance of this path to 2, add the distance of that path with 1, and whatever is your shortest path, that's your final answer. So we can do a recursive version of this, and just ask a friend, tell me the shortest path from here, tell me the shortest path from there. And how do we find the shortest path from here? Well, simply find the shortest path from there, there, and there, and add 2, 12, 23, and 13, and whatever is your smallest answer, that's your final answer from this point. But that's expensive computationally. That's like n to the n. So Dijkstra's algorithm is an efficient way to solve this problem. So let me do an example. And we'll go through a few of these. And you have a homework question on this. And I want you to work on that homework question, but I probably won't choose that one to grade. But you will see a Dijkstra's algorithm question on the final. So definitely work on it and try to make it work. But since your homework, did I make your homework due Monday or Wednesday? I think I made it due Wednesday. I gotta double check. If it's due Wednesday, then I might grade the Dijkstra's problem, because we'll be able to talk about it Monday. So yeah, we might grade that. So let's put some weights in here. And let's suppose we're trying to go from vertex A to vertex F. Yeah, it's due Wednesday. Good. Okay. I take it back then. I might grade the Dijkstra's problem. So let me put some weights on here. don't know. I'm making this up. All right. So there's some weights. I'm just trying to make it not totally obvious what the shortest path is. All right. So Dijkstra's algorithm. All right. So step 1. Assign tentative distances. And our initial tentative distance to each vertex is infinity. All right, let me grab an eraser. All right, so we're trying to go from vertex A to vertex F. What we want to do is write down a guaranteed distance to each vertex from A. And before we've done any analysis, our initial guess for how long it might take to reach each vertex is no worse than infinity. It might take less than infinity, but we know it's no worse than infinity. All right, so that's our tentative distance. But our distance from vertex A to vertex A, we know that that's a distance of 0, because we're already at vertex A. Okay, so these are tentative distances from, in this case, vertex A, because that's where we're starting from. All right, now we're going to do what's called visiting node A, which means, yeah, no worse than infinity. But remember, there's different kinds of infinity, too. Okay, so we're going to visit node A, which basically means we're just going to circle it. Once we've visited a node, we know the shortest distance to that node from our starting point. And we can do that with node A right now because we know, we can't find a distance shorter than 0. We could find a longer one. We could go 1, 5, 6, 2 and get back there. That's a total distance of 14. But we know we can reach A from A with no distance at all. So we circle that. That's our visited node. Okay, now we begin a series of steps inside a loop. So we're going to do the following. Calculate a tentative distance to each node and relax if that's a better tentative distance than what we had. All right, so what does this mean? We know we can get to vertex A in a distance of 0. Let's look at every node that we can get to from A, and using this tentative this distance of 0, let's see if we can improve our measure for how long it takes to reach each of our nodes. So for example, node B is connected to a node we visited. We can get to this node in a distance of 0. From there, it takes a distance of 2 to get to B. That tells us we can get to B in a distance of 2. So now you ask the question, is 2 better than infinity? And the answer is yes, it is. So we're going to replace this distance of infinity with a distance of 2. All right, we can also get to node D with a distance of 1 from A, while it takes 0 to get to A plus 1 more to get to D. We can get here in a total distance of 1. That's better than infinity, so we're going to relax this node as well. All right, and then we're going to visit the closest node. So we're going to look at all the nodes we haven't visited yet and say which one is closest. And we're going to mark that one as visited. If there's 2 nodes that are the same distance, it doesn't matter which one we pick. Well, what have we got? We've got 2, infinity, 1, infinity, infinity, infinity. Looks like D is the closest node. So we're going to visit that. And when we visit a node, we're basically locking in that distance. Right? We're saying, no matter what else happens, I know I can always get to node D in a distance of 1. So we're locking that in. And we're just going to keep repeating these 2 steps. So now we find a tentative distance to each node. Well, so we just added this node D. We know we can get here in a distance of 1. There's a node connected directly to it, that's E. 1 plus 5 is 6. 6 is better than infinity. Let's relax this. And there are no other nodes directly connected to D, so there's nothing else to relax. So we're done with our relaxation. Now we visit the closest node. Well, we have a node of distance 2, 6, and some infinities. Looks like 2 is closest. So we're going to visit this. That's my one that just ran out. We're going to visit this node. And then we're going to relax again. All right, 2 plus 2 is 4. 2 plus 6 is 8. Well, 8 is a longer distance than 6, so we're not going to replace a 6 with an 8. We're only going to replace a distance if it's shorter than the distance we've already found. What's happening here is we already know that we can get here from A with a distance of 6, down and over. When we do 2 plus 6 is 8, that's telling us if we go through node B, we can get here with a distance of 8. Basically, 2 plus 6 is 8. But we don't want to replace this with a longer distance, right? So that 6 there plus 2 is 8. We're going to leave the 6. Okay, so relaxing means replace the distance if it's better. All right, we're not going to do anything with nodes that we've already visited, so we don't have to look at that. There was a 4, there was an 8, so we left that as a 6, and that's it. Okay, visit the closest node. Well, there's a 4, there's a 6, there's an infinity and an infinity, so the closest node is right here. Okay, this is Dijkstra's algorithm. We just keep doing this. All right, relaxed nodes that we can reach from C. So 4 plus 5 is 9. That's better. 4 plus 1 is 5. That's better than 6. So we're going to relax this and replace it with a 5. And now visit your closest node. Well, that's going to be this one right here. And repeat your relaxation. 5 plus 2 is 7. That's a better distance. 5 plus 1 is 6. That's better than 9. So replace this with a 6. And now circle the closest node. That's F. Well, if our goal was to find the shortest distance to F, we're done. Because once you circle a node, you found the shortest distance, and the shortest distance was 6. If we wanted to continue to do all nodes, 6 plus 8 is 14. That's not better than 7, so we leave it. We circle our closest node, and we're done. And we've done a few things. We found the shortest path. We found the shortest distance from A to F is 6. We've actually found the shortest distance from A to every node. Right? 7 to here, and 6 to here, and so on. Okay, that's Dijkstra's algorithm. Now what's missing is we didn't record our paths along the way. And if we had, we could use that to figure out what the actual path is that gives us a distance of 6, for example, or a distance of 7. And so we'll do this with another example, and we'll keep track of that housekeeping. But, you know, if you have a really good memory, the way we got a distance of 6 was 2, 4, 5, 6. Whereas the way we got a distance of 7 was I think 1, 5, 6, and no, how did we get a 7? 2, 4, 5, 7. Alright, so this is a good graph. I made up a graph before class started and I printed it out on a bunch of sheets. But I like this one we just did. So let's, we've got 6 minutes left. Let's do this again, but let's keep track of path information. So there's an edge, 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 edge. And then some weights, 2, 2, 1, 6, 1, 5, 1, 2, 8, and 5. All right, so let's do this again, but let's track the information along the way. So tentative distance is infinity. Tentative distance 0. This node is visited. All right. So so what are our two steps? Relax the nodes that are adjacent to the node we just visited, and then visit the closest node. So relax the nodes that are adjacent to A. So 2 is better than infinity, so I'm going to replace this with a 2, and I'm going to list the node that I came from, which was A. And 1 is better than infinity, so I'm going to replace this with a distance of 1, and I'm going to list the node I just came from, which was A. And then visit the closest node, and relax from here. So 1 and 5 is 6. That's better than infinity, so I'll write down a 6. And I will write the path I used to get here, which was the path to the node that I'm relaxing from, which was A, followed by this node itself, D. So be thinking about how you would code this, right? If you were doing this in a computer and you've got an adjacency matrix or something for the graph, right? How are you keeping track of this information while you're adding it to a string maybe or something like that? All right, so find the closest node. So distance of 2, distance of 6. We're going to visit this node next. And then we're going to relax. 2 and 2 is 4, so this distance is 4. And the path was the path to get to B, followed by the node B. 2 and 6 is 8. That's not better than 6, so we don't relax that. And we're done relaxing. Now we visit the closest node. That looks like node C. And we relax from there. 4 and 5 is 9. That's better than infinity, so this is 9. And the path is the path we took to get to this node, AB, followed by the node itself. All right, 4 and 1 is 5. That's better than 6, so we're going to relax this with a distance of 5, and the path is AB, followed by C. And we just keep going, right? Find the tentative distance, relax nodes if the distance is better, and then visit the closest node. So we got plenty of time. Closest node, 5, infinity, and 9, so we'll visit this node and relax distances from there. 5 and 2 is 7, that's better than infinity, so this is a distance of 7. And the path was the path to E, A, B, C, and then E. 5 and 1 is 6, that's better than 9, so this is a distance of 6, and the path is the path to E, A, B, C, followed by E. Find the closest node and visit that, that's this one. Relax distances, so 6 plus 8 is 14, that's not better than 7, so we don't change that. Now visit the closest node, there's our 7. We visited all the nodes. Now we have a shortest path from A to every single node. So what's our shortest path to 7? A, B, C, E, G. Our shortest path to node F was A, B, C, E, F. All right, that's Djikstra. Awesomeness, yeah. All right, so you have a homework problem with this, and when you write this up in homework, my suggestion is, if you do this, it's really hard to know where this graph came from. So my suggestion is, make multiple copies of the graph. And, if you're just changing this distance from infinity to 1, you can cross out the infinity and make it a 1. But if I'm making two changes on this graph, do it on a separate graph. Make your first change and then move to a second graph, copy your information over and make the second change. So that as you're going through this, or as I'm going through it, it's easier to tell, what did you do from one step to the other. Because once you've got a graph that looks like this, it's really hard to know where these things came from. Right? And if there's a mistake, it's really hard to track it down. Right? Because I don't know if I did this first or that first or that first, So to do this in a way that makes it easy for someone reading it to follow your work, it helps to split it on different pages. So don't worry about that for the weekend, right? Just go ahead and work on this, see if you can figure out the algorithm, get comfortable with it. And then Monday, we'll go through this and break it out in different pieces. I'll show you how you can do this for the homework or for the final exam in particular to get full credit, especially if there's mistakes. All right, so we'll wrap that up on Friday or on Monday, and we'll start talking about languages and grammars on Monday. And then we'll have a big long break for Thanksgiving, and we'll come back and we'll finish talking about languages and grammars. We'll come back to shortest path, traveling salesperson problem, and that'll pretty much do it for the course. So we got about a week left. All right, have a fantastic weekend. Do something fun and rejuvenating because it's a nice day out there. Or come to office hours, either way. Have a good one. I will catch you next time. Thank you.